My name is B. Santhosh Kumar, Assistant Professor, Institute of Aeronautical Engineering. My subject is image processing. Today I am discussing about the topic is smoothing frequency domain filters. So in the previous session we discussed what are the smoothing and sharpening frequency domain filters. So these are the major two types of frequency domain filters, smoothing and sharpening. That is the low pass filter and high pass filter. So filtering of the frequency domain, we will revision that one. And what are the basic steps of zero pad input images f of x comma y? It is a 2m minus 1 and a q equal to 2n minus 1. The arrays of same size. The function is f of x comma y and h of x comma y into m into n. So the radix of fast Fourier transform. Here I am using fast Fourier transform. Okay. So in the fast Fourier transform, we required some m and n values, that is m equal to n equal to 512, and here I am taking k equal to l equal to 16, p equal to q equal to 1024. I am taking some examples. So what are the results of linear convolution? We are extract center of n comma n. So to multiply the input padded image by minus 1 power x plus y to center of the transform, to compute capital F of u comma v, the discrete Fourier transform of the image from 1, and the multiply capital F of u comma v by the filtering of the function h of u comma v to compute the inverse IDFT for the result, to obtain the real parts of the results and multiply the results with minus 1 power x plus y to the given filter capital H of u comma v, the filter transform function or filter function, and g of u comma v equal to h of u comma v into f of u comma v. So what is that means? G of u comma v is the output function. It is a transformation function. It is the input function. So it is the output function. It is the input function. So transformation function is I am using Fourier transform, Fourier series, fast Fourier transform, or anything. But sometimes here I am using, if I am going for the filtering technique, spatial. In the spatial, we are going for the smoothing and sharpening. So smoothing filter or sharpening filters we are using in the place of capital H of u comma v. So it is also one type of transformation technique or filtering to removing the noises or remove the edges of the original image and converting to the output image. So it is, I am taking one example here. Image A is a discrete function of m points and image B is a Fourier spectrum. It is a Fourier transform or Fourier spectrum, a discrete function with twice the number of non-zero points, and it is a Fourier spectrum. Okay, so these are the input images with Fourier spectrum. These are the outputs of Fourier spectrum. Okay, so the input is a discrete function of m points. It is the input, and what is output means it is a Fourier spectrum. It is the input of is a k points. Here I am taking 2 k points. Okay, so a discrete function with twice the number of, twice means here I am taking k, Here I'm taking 2k, that is a twice. Okay, so what is the output function here? Ak by m. Here I'm taking 2ak by m. It is the Fourier transform or Fourier spectrum of the output. Here another example, it is a low pass filter, it is a low pass filter, and it is a high pass filter. These are all under frequency domain filtering. Okay, so here h of u comma v is a transformation function. It is a one coordination is h, another coordinator is v. Here one coordinator is u, it is one v, and it is the origin. Here the transformation technique. Here what is the transformation technique means? I am using high pass filter. So what is the transformation technique means? Here low pass filter, high pass filter. Okay, so here a two-dimensional low pass filter function, and result of the low pass filtering of the image. Here a two-dimensional image, 2D image with high pass filter, and the result of high pass filtering of the image, high pass filter image, low pass filter image. It is one example. So these low pass filters and high pass filters are the frequency domain filtering techniques. So there are the majorly two types are there in the frequency domain. That is a low pass filter. Another one is a high pass filter. So what is the need of low pass filter and what is the need of high pass filter? We will discuss now. So here I am taking one frequency domain equation, that is since h of x comma y, it is the output function h of x comma y we are obtaining from the response of the frequency domain filter. So f of x comma y into h of x comma y. Here h of x comma y is the transformation function I am taking. So spatial domain frequency is a general, is a faster than frequency domain. So some cases it is a desirable to generate spatial domain mask that approximates a given frequency domain filter. So the following procedure is one way to create these masks in a least square error. To recall that filter processing in a frequency domain, which is product of filter and function, becomes convolution of function and filters in spatial domain filters. Here the restriction of effect creates an end-to-end convolution of mask h with Fourier transform of capital H of u comma v equal to 1 by n, summation x equal to 0 to n minus 1, summation y equal to 0 to n minus 1, h of x comma y into e power minus j 2 pi ux plus vy by n. So here I am taking output function. It is the transformation function. With I am applying the input function. Okay. So to find the coefficients of h of x comma y such that the mean square error is minimized. So we are considering the filter transformation technique. H of u comma v is equal to 0 comma 1. The limits are 0 1. If it is 0, then u comma v equal to m by 2 comma n by 2. If it is 1, it is otherwise. I am going to the filter set of f of 0 comma 0, the 0 and leave the other frequency components. Such a filter is called notch filter since it is a constant function with a hole or notch 0. So when I am going to the h of u comma v, so already here discussed here h of u comma v equal to output function. So this function has the two limits are there. If 0, what is happening? If 1, what is happening? If 0, u comma v equal to m by 2 comma n by 2. If it is 1, what is happening means it is working as a notch filter, or it is a constant filter, or it is going to the origin. So it is also like a homomorphic filter. What is a homomorphic filter? An image can be modeled mathematically in terms of illumination and reflection of the following: f of x comma y equal to I of x comma y into r of x comma y. So the input function f of x comma y equal to I of x, y into r of x, y. Here, capital F means the Fourier transform of the input function. So, what is the Fourier transform? Capital F of input function f of x, y. The Fourier transform function of the L of x, y, comma, Fourier transform of r of x, y. So, what is the z output function? Z of u, v equal to L of u, v plus r of u, v. So, here the input function, if I am applying the Fourier transform, what is output means capital Z of u, v, capital I and capital R. After applying the Fourier transform, it is showing as a capital letters of I, v, I of u, v plus r of u, v. So, in the frequency domain, a digital image is converting into the spatial domain to the frequency domain. In the frequency domain, image filtering is used for image enhancement for a specific application. A fast Fourier transform is a tool of the frequency domain used to convert the spatial domain to the frequency domain. So, here I am using smoothing and sharpening images. So, what is the smoothing of the image? It is a low pass filter to implementing, and for sharpening of image is a high pass filter for implemented. So, both the filters are implemented as an analyzed for ideal filters, Butterworth filter and the Gaussian filters. Okay. So, the frequency domain is a space which is defined by a Fourier transform. The Fourier transform has a very wide of applications in image processing. Frequency domain analysis is used to indicate low signals and how the signal's energy can be distributed in the range of frequencies. And the basic principle of frequency domain analysis in the image filtering is to compute 2D discrete Fourier transform of the image. So, here I am using two types of filters, that is a low pass filter and a high pass filter. Okay. So, low pass filter and high pass filters are the two types of frequency domain filters. So, these are the frequency domain filtering two types, low pass filter and high pass filter. In the low pass filter, it is a smoothing filter. High pass filter is a sharpening filter. So, in the frequency domain, digital images are converting from spatial domain into the frequency domain. In the frequency domain, image filter is used for image enhancement for a specific frequency domain. And the fast Fourier transformation is a tool that the frequency domain used to convert the spatial domain into the frequency domain. So, smoothing of an image is a low pass is implemented of and sharpening of an image. High pass filters are implemented when both the filters are implemented to analyzing of the ideal filter, Butterworth filter and the Gaussian filters. Okay, these are the advantages of low pass filters with spatial and domain and frequency domain. So, the frequency domain is a space which is defined by Fourier transform. Fourier transform has a very wide of applications in the image processing. Frequency domain analysis is used to indicate how signal energy can be distributed in a range of frequency. So, the basic principle of frequency domain analysis is the 2D discrete Fourier transform of the image. So, Fourier transform is a tool for image processing. Okay, but it is a decomposition of image into the sine and cosine components. The input image is a spatial domain and the output image is a Fourier or frequency domain. But the Fourier transform is used in a wide range of applications such as image filtering, image compression and image analysis in the image construction. So, what are the image transformation means? It is a tool of image processing where I am using it is the decomposition of the image into the sine and cosine components. The input image is a spatial domain and the output is representing in the Fourier or frequency domain. But the Fourier transformation is a wide range of applications such as image filtering, image compression and image analysis and image reconstruction. These are the Fourier transforms. The formula for Fourier transformation It is a Fourier transformation, capital F of u comma v, summation minus infinite to infinite. It is the input function f of x into e power minus z 2 pi ux into dx. Okay, it is a input image. Summation, integration, minus infinity, infinity, capital F of u into e power j 2 pi ux into dx. Okay, it is a Fourier function. It is a input image. So the Fourier transform of capital F of u is equal to input function. First we have to know what is the input function. Input function is small f of x. It is the integration of minus infinity to infinity capital F of u into e power j 2 pi ux. What is f of u comma v is nothing but here it is a Fourier transform function. So if I want to go for the Fourier transform equal to integration of minus infinity to infinity of input function small f of x into e power minus j 2 pi ux into dx. So what is a low-pass filter? Low-pass filter is nothing but it is a smoothing filter. Already we know that how many types of frequency domains are there? So low pass filter is a smoothing and a high pass filter is a sharpening filter. So a low pass filter or smoothing filter is used to pass low frequency signals. A strength of the signal is reduced and the frequencies which are passed is higher than the cutoff frequencies. The amount of strength reduced for each frequency depends on the design of filters. Smoothing is low pass operation in the frequency domain. So here low pass filter is nothing but a smoothing filter. These are all frequency domain. These are the techniques of frequency domain. But what is the use means? Low pass filter is a low frequency signals. The strength of the signal is reduced and the frequency which are passed is higher than the cutoff frequencies. The amount of strength reduced for each frequency depends on the design of the filter and the smoothing is low pass frequencies in the frequency domain. So when I am using the ideal low pass filter, it is the cutoff all the high frequency components of Fourier transformation. But below the transformation function, all the ideal low pass filters, the ideal low pass filter, ILPF, ideal low pass filter is the simplest low pass filter and that's cut off all the high frequency components of the discrete Fourier transform that are at distance greater than a specified distance d naught from the origin of the centered transform. Okay. So the ideal low pass filter is used to cut off all the high frequency components of Fourier transform. Below is the transfer function of an ideal low pass filter. The ideal low pass filter ILPF is the simplest low pass filter that cuts off all the high frequency components of the discrete Fourier transform that are at distance greater than a specified distance t naught from the origin of the centered transform. Here I am applying the ideal low pass filter. Previously we discussed low pass filter and high pass filter. Here about ideal low pass filter ILPF is the simplest low pass filter for the cutoff frequencies. Here I am taking one equation, capital H of v comma v. What are the conditions? If it is 1, what is happening? If it is 0, what is happening? If it is 1, capital D of u comma v means Fourier transform of the function. D of u comma v is less than or equal to d naught. If it is 0, capital D u comma v is greater than d naught. So the d naught is the cutoff frequency. Already we know that. What is the when we are using cutoff frequency means? When I am using it means here already we discussed ideal low pass filter. If it is a ideal low pass filter, then I am applying the cutoff frequency. So the cutoff frequency means here I am applied ideal low pass filters. So capital D of u comma v equal to square root of u minus m by 2 whole square plus v minus n by 2 whole square. Already m by 2 comma m by 2 the limits we discussed in the filtering of the frequency domain. But here one example, it is an input image, it is an ideal low pass filter, and it is an inverse low pass filter, and inverse low pass filter of radial cross section. So ideal low pass filter, it is an ideal low pass filter, it is a ideal low pass filter of the image. Okay, when applying the mask technique here, filtering technique here, ideal low pass filter of the radial cross section. Okay, these are the different conditions are there for the ideal low pass. But when I'm using ideal low pass means when it is using the cutoff frequencies, it is using for the cutoff frequencies. So ideal low pass filter indicates that all frequencies inside a circle of radius d0 are passed with no attenuation or no attenuation, whereas all frequencies outside the circle are completely attenuated. So it is one example of ideal low pass filter. It is an ideal low pass filter. So it indicates that frequencies inside a circle of radius d0 and passed with no attenuation, whereas all frequencies outside the circle are completely attenuated. It is a inverse low pass filter or ideal low pass filter. So it is one example of original image, it is the input image, and it is the output image. So what is the difference means, here it is the input is the original image, output is a Fourier spectrum, means we are applied mask here. It is results the applying the ideal low pass filter with the previous cutoff frequencies. So when I have to apply the cutoff frequencies, then I will use ILPF. Okay, it is the input original image, it is a Fourier spectrum output. It is another example. Here the below figure shows a gray image with its Fourier spectrum. So these circles superimposed the spectrum representation of cutoff frequencies 5, 15, 30, 8 and 230. I am taking some cutoff values are 5, 15, 30, 80 and 230 are the cutoff frequencies of the image. So what is happening? So there are it is an input image. These are the different cutoff frequencies. So the cutoff frequency, it is another cutoff frequency, it is another cutoff frequency. So in the different cutoff frequencies, what is the image showing? Okay, when I'm going for the cutoff frequencies very less, it is showing as a blurring, and we are increasing the cutoff frequencies when it is looking good. Okay, and we can see the following effects of ideal low pass filter: blurring effect, which decreasing the cutoff frequencies; ringing effect becomes a finer, that is decreases the cutoff frequencies and increasing. Okay, here it is the original image, that is the input image, original image, and B2F. Here I am taking some B2F images. Ideal low pass filter with the cutoff frequencies 5, 15, 30, 80 and 230 respectively. So these are the cutoff frequencies. Okay, when you are going to the different images, okay, when we are going for the different cutoff frequencies, the image showing blurring. Why? Because we are increasing the cutoff frequencies. So what is the use of ideal low pass filter means? To blurring effect which decreases as the cutoff frequency is increasing. Okay, so when I am increasing the cutoff frequency, increasing the cutoff frequency, decreasing the blurring. That is a concept. Blurring effect which decreases the cutoff frequencies. Ringing effect which comes finer, that is decrease as the cutoff frequencies increasing. So the Gaussian low pass filter GLPF, the GLPF with cutoff frequencies D0 is defined as the Gaussian low pass filter, and the Gaussian low pass filter as an image, Gaussian low pass filter of radial cross section. Okay, here the inputs are U comma B, and it is a function capital H of U comma B, and B is the low pass filter or Gaussian low pass filter. It is a Gaussian low pass filter of radial cross section of the image. So here ideal low pass filter and Gaussian low pass filter, the transformation techniques does not have a sharp transition that establish a clear cutoff between passed and filtering frequencies. Instead of Gaussian low pass filter has a smooth transition between low and high frequencies, but The figure shows the result of applying Gaussian low-pass filter on the image with the same previous cutoff frequencies. Okay, when I'm applying the cutoff frequencies, then I have to use ideal low-pass filter. But here, why the need of Gaussian low-pass filter? Here, one example, it is the original image. Where it is means it is the original image. Okay, it is the image B, C, D, E and F. So original image is A and B to F results of Gaussian low pass filter of the cutoff frequencies 5, 15, 30, 80 and 230. So when I am increasing the cutoff frequencies, when we are decreasing the blurrings, okay, it is one example of Gaussian low pass filter. It is showing blurring image. Okay, so it is nothing but a I'm applied the filtering. When I applied the filtering, okay, how much blurring is there? Okay, depends on your using the filter type. It is showing as a sensitivity or blurring of the image. Okay, here it is a Gaussian low pass filter. Okay, so here A is the original image, B to F results of Gaussian low pass filter with cutoff frequencies. Okay. So we can see that the following effects of Gaussian low pass filter compared to inverse or ideal low pass filter: smooth transition in blurring as a function of decreasing the cutoff frequencies, no ringing effect, smoothing low filters useful in applications. For example, Gaussian low pass filter can be used to bridge small gaps in broken characters by blurring as shown below. This is a useful characters of recognition. Okay, here it is a Butterworth low pass filter. So what is the use of Butterworth low pass filter? It is using to remove the high frequency noises with very minimal loss of signal components. So what is a major advantage of ideal Butterworth filter means? Use it to remove high frequency noises with very minimal loss of signal components. Capital H of U comma V equal to 1 by 1 plus D into U comma V by D naught power 2 power N. It is one example of Butterworth low pass filter. Here I am using filter with mask. Okay, so these are the smoothing frequency filters. It is nothing but a low pass filter. So the frequency domains are the two types are there. That is a low pass filter and high pass filter. But here I am using frequency are the low pass filter is nothing but a smoothing. High pass filters are the sharpening. So in this session we discussed smoothing of low pass filter. In the next session we will discuss high pass sharpening filters. So when I am using the Fourier transform, this is the equation. In the frequency domain, the spatial domain is converting to the frequency domain, and the frequency domain image filtering are used for the image enhancement of the specified filter. In the frequency domain, a space which is defined by Fourier transform. The Fourier transform has a very wide applications in image processing. So frequency domain analysis used to indicate how the signal energy can be distributed in the range of frequencies. By the basic principle of frequency domain analysis is image filtering is to compute 2D discrete Fourier transform of the image. So the Fourier transform is a tool of image processing for the sine and cosine components. Here one example or one equation for formulating the Fourier transform. Capital F of U is a Fourier transform equation. For which one we are applying the Fourier transform is for the input image. For the input image f of x, we are applying the Fourier transform. Capital F of U equal to integration of minus infinity to infinity small f of x into e power minus j2 by ux, and input function f of x equal to integration of minus infinity to infinity capital F of U means Fourier transform function with e power j2 by ux. What is the difference means? Only indications. So already we know that smoothing is a low pass filter. So what is the use of low pass filter means? To reducing the frequencies which is passing the only low pass filters. We are accepting only low pass signals and stopping the high pass filters. And it is also using for the cutoff frequencies. The amount of strength reduced for each frequency depends on the design of the filters. So smoothing is low pass operation in the frequency domain. The ideal low pass filter is used for the cutoff frequency of the high frequency components of the Fourier transform. So what is the use of ideal low pass filter? It is a simplest technique for the cutoff frequencies. It is a simplest technique using for the cutoff frequencies, and all high frequency components of the discrete Fourier transform that are at a distance greater than a specified distance d naught from the origin of the center transform. So here ideal low pass filter is using for the cutoff frequencies. Here one equation for capital H of u comma v, when we have two conditions 1 and 0. If it is 1, d of u comma v is less than or equal to d naught. If it is 0, d of u comma v is greater than or equal to d naught. Okay, it is the ideal low pass filter. These are the two dimension u and v are the two dimensions, and it is a function capital H of u comma v. And ideal low pass filter image, it is a ILPF image. It is a ILPF radial cross section. So ideal low pass filter indicates that all frequencies inside a circle of radius d naught are passed with no attenuation, whereas all frequencies outside the circles are completely attenuated. It is one example of ideal low pass filter with cutoff frequencies. Here I am using ideal low pass filter with the different cutoff frequencies are there. Here input image, that is the original image, and it is a Fourier spectrum. Here one example of cutoff frequencies, that is 5, 10, 5, 15, 30, 80, 230 are the cutoff frequencies. What is the input image is the original image. Output images are the cutoff frequencies. Here I am applying the Gaussian low pass filter for ideal low pass filter to getting the exact cutoff frequency values. Here there are the different cutoff values are there. So in this for these cutoff frequencies I am using ideal low pass filters and a Gaussian low pass filters for cutoff frequencies. Okay, here ILGF and GLPF are the transformation functions, does not have sharp transition that establish a clear cutoff between paused and filtered frequencies. Instead of Gaussian low pass filter, a smooth transition between low and high frequencies. The figure shows the results of applying Gaussian low pass filter on the image with the same previous cutoff frequencies. These are the examples of cutoff frequencies, ideal low pass filter. In the next we will discuss sharpening or high pass filtering of the frequency domain filters. We will discuss in the next session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.